Hi folks, been a while. Now foam roller's been lost. So what we plan to do here is the Leaving Cert calculations from 2021 to 2019 on acids and bases. So generally question 7 of the Leaving Cert papers. So the first thing here, define an acid according to the theory of Arrhenius. So these things they must just learn off. Look at your book, look at your notes. An Arrhenius acid is a substance that dissociates in water, forming hydrogen ions. H plus ions or protons if you wish. A Bronsted-Lowry acid is a proton donor. State one limitation of Arrhenius' acid and base theory. So in Arrhenius' theory, his reactions were confined to acid-base reactions. So what you could say there is not all acid-base reactions take place in water. What is a conjugate acid-base pair in the Bronsted-Lowry theory? A conjugate acid-base pair is an acid and a base that differ by the presence or absence of a proton. Or simply put, if you look at the marking scheme, it's an acid and a base that differ by a proton. Distinguish between a strong acid and a weak acid. Now it doesn't say whether we're going to be using Bronsted-Lowry's theory or Arrhenius' theory. So what I would do there is chat about both. So in terms of Bronsted-Lowry theory, a strong acid is a good proton donor. And in terms of Arrhenius, an Arrhenius acid dissociates into hydrogen ions. The stronger the acid, the more readily dissociates, or the fully it dissociates into hydrogen ions. So fully dissociates, breaks up to these hydrogen ions. And in terms of the weak acid, it's just the opposite of that. So instead of being a good proton donor, you've guessed it, it's a poor proton donor. And in terms of Arrhenius, it only partially or slightly dissociates. Into your hydrogen ions. So they're your standard questions to ease you, and you have to learn those. Now we're into the tough ones, because the questions in acids and bases are difficult. So see there. Sulfuric acid is a strong dibasic acid. Write a balanced equation to show that the conjugate base of sulfuric acid acts as a Bronsted-Lowry acid in water. Now there's two ways you can do that. The first way, you'll have to work out the conjugate base of sulfuric acid. So option 1, the way to work that out, for a conjugate acid, you add a proton. A for acid, A for added. So for the conjugate base, instead of adding the proton, we're just going to take away that proton. So minus my H plus, it's lost a hydrogen, so I'm down to 1 hydrogen, and your SO4, and it's lost a plus charge, so it's minus. Another way you could have got that is taking your sulfuric acid. We're looking at it dissociating in water. It's a strong acid, so it's a good proton donor. So it's giving away my H plus. So what are we going to be left with on the right hand side? HSO4 minus, as we had there from the other method, and H3O plus, our hydronium ions. So that's the first thing. We've now got our conjugate base, which is HSO4 minus. We've got to say, write a balanced equation to show the dissociation, part C. Write a balanced equation to show that the conjugate base, which is our HSO4 minus, acts as a Bronsted-Lowry acid in water. So both methods will involve you doing this. I've got my conjugate base, my HSO4 minus, I'm adding my water. They'll not be fussy at these arrows. Weak acid, you'll put in your reversible reaction arrows, irrelevant. It's an acid, so once again, it's a proton donor. So what are we left with on the right hand side? SO4, it's lost that hydrogen, it's lost another plus charge, SO4 2 minus, our sulfate anion, and H3O plus. Job's a good one. D part 1. Write a balanced equation to show the dissociation into ions in water of a weak monobasic acid. Once again, this is in water. We've got a weak monobasic acid, which could easily be HCl or HNO3. So in general terms, I've got my HA. It's reacting in water. It's weak. But once again, since it's an acid, it's a proton donor. So I'm giving away that H+. So what I'm left with on the right hand side is A- plus H3O+. That's it, done. If HA is 1.5% dissociated in a 0.1 molar solution, find the concentrations of H3O+ and A- in moles per litre. So we look at these, they're all in a 1:1:1 ratio. Now they're telling me I'm starting off with 0.1 molar solution of my HA. Now it's going to dissociate and it's 1.5% dissociated. So all I've got to do there is go 0.1 by 1.5%, throw that into the calculator, whatever answer it spits out, that's my concentration of my H3O+ ion and my A- ion as well. So throw it into your calculator, shift in the left bracket, or your percentage button could be down the bottom. We have 3/2000 or 1.5 by 10 to the minus 3. Now if you didn't like that number, you didn't understand it, to get rid of the scientific notation, shift mode, 8 for Norman, and then 2, and we see there that's 0.0015. Now a lot of the time in these acid bases, it is good to have it in your scientific notation, because you'll be getting things like 10 to the minus 6, 10 to the minus 7 and so on. And the next one, part 3, we're getting through it rightly. Calculate the pH of the 0.1 molar HA solution. So the formula that we need to know for pH is the negative log to the base 10 of the hydrogen ion concentration. Now the hydrogen ion is the same as our hydronium ions, our H3O+. Now we worked that out to be, in the previous one, 0.0015 or 1.5 by 10 to the minus 3. So we just simply minus log to the base 10, whatever one you want, throw it in, and we'll know we're right because it should be an answer less than 7 because it's acidic. So I'll press minus. Only thing there is going to be answer minus. Delete that. Minus log, and log to the base 10, or our log button here is to the base 10, so minus log answer, and we get 2 numbers after it, decimal point, say 2.82. And the last thing here, hence or otherwise calculate the value of the acid dissociation constant Ka. So Ka, like our equilibrium constants, it's the products over reactants in moles per litre. That's what the square brackets mean, in moles per litre. So Ka, we're ignoring our H2O because that always has a constant value. So it's the right hand side, our A-. So I'm just taking it from here. Times our H3O plus or H plus over our HA. So once again, we've just changed our Kc to Ka because H2O always has the same value. We're looking at purely in terms of the acid. Throw in the values that we had, our 0.0015 of each of those. Or you could have wrote that as 0.0015 squared over our HA, which is 0.1. Because it did tell you, just assume that it's 0.1 so you don't have to take it away or anything. Put that into your calculator now, and jobs are good. So I'm just going to write it as squared, purely out of laziness, over 0.1, 9 over 400,000. Press that SD button, see what I mean? If we want it back, shift, mode, 8 for Norman, and it must be with a 1. 2.25 by 10 to the minus 5. And that's our value of Ka. Now, we'll do another one here. It was 2021. Have a look now at 2020. Similar story. They often break you in easy with the definitions, and to call a spade, it's inexcusable not to learn them. Like. So 7a, well, according to Bronsted-Lowry, what is an acid? An acid is a proton donor. How does this theory distinguish between a strong and a weak acid? So the same thing once again, except this time suppose it's this theory. A strong acid is a good proton donor, whereas a weak acid is a poor proton donor. What is the conjugate acid? Now, when I'm doing my acid, A for acid, A for added. That's the one I always work with. So to work out the conjugate acid of HSO4 minus, I'm adding on a H plus. A for acid, A for added. So now I've got two hydrogens, and the SO4 minus 1 plus 1 cancel each other out. So it's H2SO4, sulfuric acid. And for the second bit here, conjugate base, instead of adding on a H plus, I'm going to take away a H plus, and I've lost the hydrogen, so I've got SO4, 2 minus. The same as the previous one. That's sulfate, anion coming up again. Now, next bit. When carbon dioxide is pumped into still mineral water becomes sparkling water, information shown in the table is given on the bottle of sparkling mineral waters. Describe how you could test this sample for the presence of your sulfate ion. So there's your test for anions thrown into these as well. So mixing up your water, your test for anions and acids and bases. Now you have to learn those. Your test for sulfate, you had this thing known as barium chloride, BaCl2. You get a white precipitate of BaSO4, barium sulfate. And the thing about this, learn these a bit better. My goal here is just to do the calculations. There's one I in each. So you get a precipitate for your sulfate and your sulfite. The only way I could remember it when I was in school there's one I in each. So what I mean by that, there's no I in sulfate. So one I in each. That precipitate is insoluble. There's the I in this, and hydrochloric acid. And sulfite, it's the exact same. You add your BaCl2, my barium chloride, you get a white precipitate, this time of BaSO3. It's sulfite, it's got the I, so its precipitate is soluble. So maybe write that down, pause the video, so you can get your head around it. D there. The pH of sparkling water is 5.6, while source water was 7.2. So there's me sparkling, there's me source. Calculate the H3O plus concentration of the sparkling water. So there's a few formulas you need to learn, and this, the one for your pH, minus log to the base 10 of your hydrogen ion concentration. Now that is the same. If you see H plus, it's your same as H3O plus. So don't be getting confused in that. I often have the tendency to write down H plus. So fill in your pH of your sparkling water, which is 5.6. It's minus log to the base 10 of H plus. Here, what we want to do is get rid of that minus, bring it over to the other side, or switch sides if you wish. And whatever way you wish to do these, say I'm an awkward sort of fool, I use a rhyme. Liverpool beats Newcastle, powerful from the higher level maths. B stands for my base, so 10. My power is minus 5.6, and that's equal to my number, or my hydrogen ion concentration. Now, I hate Liverpool, so say Leeds, Leicester, or anything. The easier way, what you'll just see in your maths book, is the anti-log, just above your log button. So you got to press shift, log, and the thing you have to remember, people always forget, put in your minus before your pH. And we have 2.51, say by 10 to the minus 6. Which is right, because it's acidic, it has to be less than by 10 to the minus 7. Or bigger than, 10 to the minus 7. Now your hydroxide ion concentration of your source water. So on this, once again, your pH is minus log to the base 10 of your hydrogen ions. So what we're going to do here is work out our concentration of our hydrogen ions first of all. We're going to throw this into our ionic product, our Kw, and from that, that'll enable me to work out the concentration of my hydroxide ions. So pH is 7.2 minus log to the base 10 of my hydrogen ions. Bring that minus across. And now do my anti-log, or use my rhyme. Leeds beat Newcastle. Powerful. The anti-log's probably easier. So, and 6.3 by 10 to the minus 8. Now we know that's not our hydroxide ion concentration, as it's smaller than by 10 to the minus 7. That means 0.7 zeros before it, 6.31. So a lot of people would have left their answer like that. But in this, the way I would do it is use my ionic product. Kw is H plus times OH minus. Now at 298 Kelvin, or room temperature, 25 degrees Celsius, that has a value of 1 by 10 to the minus 14. We're going to fill in my H plus to be 6.3 by 10 to the minus 8. And now my OH minus will work out. Now that's just a number. It's a brute of a number. But think to myself, if I had 2x equals to 8, how would I get that x on its own? My x being my hydroxide ion concentration. I divide. Same thing here. To get this on its own, divide by the number stuck onto it. That'll give me my hydroxide ion concentration. I can simply use that answer in my calculator. So fraction button, 1 by 10 to the minus 14, divide that by answer, and I get 1.58 by 10 to the minus 7. So since it is basic, it's going to have a bigger concentration of my hydroxide ions compared to my hydrogen ions. Now that is tough. Call a spade, that's a difficult question. You know, that puts beef in your back. But if you split it up, 6 marks for the first one, I'd say 6 for the second. You probably got 3 for this here, only guessing. And your acid base indicator, which is a weak acid, may be represented by HA. So it's a weak acid, so it only slightly dissociates. Got to be using these arrows. They'll not be fussy, I'm sure. The indicator is red in its undissociated form and yellow in the form A minus. So what we've got here, I've got my acid base indicator. It's a weak acid, so it's going to dissociate into hydrogen ions, H plus. What are we left with? A minus. And it's red in its undissociated form, and it's yellow in its dissociated form. Calculate the pH of an aqueous 1.5 by 10 to the minus 3 solution of the indicator, which has an acid dissociation constant of 4 by 10 to the minus 4. Now the way I'd be looking at this, pH, once I see pH, I'm writing down this formula. Now in order for me to work out the pH, I need my hydrogen ion concentration. And the way we get that is from the information they give me. The hydrogen ion concentration, I'll do it over here, a bit messy, is the square root of gamma, Ka times Ma, gamma, chameleon. So H plus, my Ka is 4 by 10 to the minus 4, and my Ma is 1.5 by 10 to the minus 3. Throw that in your calculator. So square root of Ka by Ma. We have 7.75 by 10 to the minus 4. 7.75 by 10 to the minus 4. Now, even if you forgot and you thought that was the pH, you'd know that wouldn't look right. Because it's a very, very, very strong acid there, with a pH of 0.0007775. You know, so something else would click. You're like, geez, that must be that gamma thing. So now we're going to horse this in to this here. So pH minus log to the base 10 of 7.75 by 10 to the minus 4. So minus, remember, once you press the minus, you've got to delete both of those. Minus log answer 3.11 is my pH, and that seems more the story there. It's below 7 and not at the lower end of the scale. Right, F part 1. Write an equilibrium equation for the dissociation of the indicator in water. So the indicator is HA, in water, H2O, weak acid using that. But since it's an acid, according to Bronsted-Lowry, it's still a proton donor. So what I'm left with is A minus plus H3O plus. Job's a good one. What is observed when a few drops of the indicator are added to the solution of a strong base? Now, if we add a base, this brings in Le Chatelier from your equilibrium chapter. So if we add in a base, we increase the concentration of our hydroxide ions. Now another way of saying that is, in this here terms, in terms of the acid, we decrease the concentration of hydrogen ions. Remember now, let's tell you, when a system at equilibrium is subjected to a stress, the system responds in such a way. So what are we going to do here? The system responds in such a way as to increase the concentration of hydrogen ions. How are we going to increase the concentration of hydrogen ions? We're going to shift that equilibrium to the right. Sorry about this. This will test if you're watching it. Grapes. So bring back the foam roller. System responds in such a way as to increase the concentration of hydrogen ions. Equilibrium shifts to the right. That just means go to the right hand side. And we get the yellow colour. That's difficult, but if you're struggling that, you'll need to revise Le Chatelier and these stresses, so concentration, pressure, and so on. You get a yellow colour. I may as well. We'll try 2019 when we're here, maybe do it quickly. Because otherwise it just means another video. So section 3. And that's as long one. I'm going to stop. Do 2019 and another one.